Jessica Birungi, and I'll be taking you through the basic inferential statistics for public health professionals. You can feel free to check out my LinkedIn, and a lot of statistics is on that page. I discuss a lot of statistics. So if you're interested in diving deeper, you can always check out my page. So many articles on there. Our learning objectives for this course are to understand the key concepts in inferential statistics, and then get to know the difference between the descriptive and inferential statistics, and also explore the common statistical methods used for inferential statistics in public health research. I hope all of us were able to go through, if not attend, the previous presentation that I made on descriptive statistics. So what exactly are inferential statistics? So inferential statistics use a sample of data drawn from a population to make inferences or predictions or draw conclusions about a population that is under study. So unlike descriptive statistics, which summarizes data, like we said in the previous class, inferential statistics allow us to make conclusions beyond data that we observe, as descriptives only give us a brief summary of the sample that we have. But inferential statistics go ahead and help us draw conclusions from the data that we have about the population under study. So what are the key features of inferential statistics? We have generalization. We are able to generalize our findings or draw conclusions about a larger population based on our sample from which the population was drawn. And we are able to do hypothesis testing to test whether the observed data or our sample supports a specific claim or hypothesis, and to also estimate population parameters. We are able to estimate parameters based on the sample population parameters based on the sample statistics that we have. So usually, due to so many research concerns, we are not able to study the entire population. So in order to make references about maybe teenage girls in Southern Sudan, on whether they are getting pregnant or not, we have to draw a sample of teenage girls in Southern Sudan from the entire country that is representative of all the teens in South Sudan. So from this sample, we do our statistics, and those statistics that we get from the sample are the ones that we use to draw conclusions. I think this R is a bit misleading. To draw conclusions about the population of the teenage girls in Southern Sudan. So due to financial constraints, usually a sample is drawn and then that sample is studied for the outcome of interest. And then from that sample, we are able to make conclusions about the entire population. So let's look at some key concepts in inferential statistics. So let's look at what we mean by a population and then a sample. So a population is usually who or what you want to study. A bigger group of what you want to say something about. So it is usually a bigger group, and we usually draw a very small sample that is representative of the bigger group. Okay. So a population is usually a cluster of people, events, items, things, or any other phenomena in which you are most interested in. And then a sample is a subset or a smaller group of that population or that target population. I hope we are still following.
Yeah.
So next, let's look at the probability. So probability forms the foundation for making inferences about a population based on the sample data. It is usually the measure of the likelihood that a specific event will occur. So it allows us to make an estimate or to estimate the likelihood of various outcomes, to assess different risks, and to make data driven decisions from the sample. And it usually ranges from 0, representing the impossible event, to 1, representing any event occurring. So probability is usually given by the number of favorable outcomes over the total number of possible outcomes. Let's look at an example. So if 10 out of 100 patients in a sample, looking at our example, and as stated in our formula, we shall have to divide 10 positive patients out of the total number of patients, because our favorable outcome is positive and we have 10 patients who are testing positive for this disease under study. So we shall have to divide 10 out of 100 patients, and it will give us 0.1 or 10%. As simple as that. And in current situations, we do not have to do that by hand. There are so many statistical softwares that help us calculate probabilities. So let's look at another scenario. So a public health researcher wants to determine the probability of selecting a patient who has diabetes from a sample population of 1,000. I hope you're following.
Yeah.
So we have a population of 1,000 patients, and 150 people have been diagnosed with diabetes. Okay, so we want to determine the probability of selecting a patient who has diabetes from this sample. Yes, Regina.
Let me try, madam.
It's
You
okay.
say we have 1,000 patient, right?
Yes.
Then out of 1,000, 150 turn to be diabetic patient.
Yes.
Okay. So it's the same like this. We just divide 150 over 1,000.
And what do we get?
Then we get the diabetic patient now out of that. The
Okay,
the
so we shall
person.
have a 15% probability. Thank you very much, Regina,
You're welcome.
of randomly selecting a patient with diabetes from this population. So probability is, as I said, a foundation of making inferences. And if you're to write down what you really need to dive deeper into to understand inferential statistics, it should be probability. It's a powerful tool in public health, and it helps professionals make informed decisions about risks, treatment, population health trends, and it allows you to make accurate predictions. Okay? It plays a very key role in designing effective interventions. So if you're to write down in something that you really need to deep down understand, that should be probability. So let's look at some common probability distributions in public health. Um, Probability distributions describe how the probabilities of different outcomes sample are distributed for a given variable. So we have the binomial distribution, and the binomial distribution is used for binary outcomes, the yes, no, success, failure variables. And an example could be person being vaccinated or not, teenage pregnancy or not teenage pregnancy, cancer or no cancer, diabetic, not diabetic. So those are some of the binary outcomes under which the binomial distribution can be used. So let's move on to the next distribution. We have the normal distribution, which is a continuous distribution that describes data with a symmetric bell-shaped curve. So it is the common distribution. I didn't include the figure, but you can always go and look out for the normal distribution. Usually it is used for continuous variables like height, cholesterol levels, and these variables in a population usually follow a normal distribution. So lastly, we could look at the Poisson distribution, which is used for modeling the number of events occurring with a fixed interval of time or space. This could be the number of new cases of disease, number of hospital beds, number of people retained in care, number of HIV patients retained in care, number of road accidents in a given period of time. So this distribution is usually modeling the count of an outcome. Okay.
Okay.
So thirdly, let's look at the sampling error, which gives the difference between a sample statistic, usually known as a measure based on a sampled data, and then the true population parameter, which corresponds to the measure of the entire population. So this sampling error occurs because we are working with a sample, which is only a subset of the entire population. And the sample may not perfectly represent the population. So this sampling error accounts for that imperfection of the sample to represent the entire population. Next, let's look at the common inferential statistical methods. Let's begin with hypothesis testing. So, hypothesis testing is a statistical method used to make decisions or inferences about a population based on sample data. So it evaluates whether there is enough evidence to support or reject a specific claim about a population parameter. For example, mean, proportion, among others. So we usually have two types. We have the null hypothesis and then the alternative hypothesis. So the null hypothesis states that there is no effect or no difference. So it represents the default assumption under study. For example, if you're trying to study the effectiveness of a new vaccine, so our null hypothesis would be that the new vaccine does not reduce the incidence of disease. And the alternative hypothesis is usually the hypothesis that there is an effect or there is a difference. And it is what the researcher aims to support. Okay? So it is usually the alternative hypothesis that the researcher aims to support, and the null is the opposite. Okay? So, what are the common errors in hypothesis testing? We have the type 1 error, which is also commonly known as the false positive, and it occurs when the null hypothesis is rejected when it is actually true. And the type 2 error, usually known as the false negative, occurs when the null hypothesis is not rejected when it is false. So let's look at the common types of hypotheses. Hypotheses is used in public health. Hypothesis tests used in public health. So we have the common t-test that compares the means of two groups. For example, testing whether the average blood pressure of two groups is significantly different. So we usually look at two categories, two groups, and we study if their means are different under the t-test. Simple as that. That is the basic. So for the chi-square test, it compares proportions between groups. For example, testing whether the proportion of vaccinated individuals differs significantly between the two cities. The proportion of vaccinated individuals maybe in rural areas differs significantly from the proportion of vaccinated individuals in urban areas. Yeah, and as simple as that. And lastly, we have the ANOVA test, which compares means across more than two groups. For example, comparing the mean cholesterol levels across age groups, across 3 age groups. Lastly, let's look at the regression analysis, which tests relationships between variables, either by variable when you're testing a single variable or multivariable when you're testing relationships between variables and then how they affect each other in the same model. So, for example, assessing whether smoking status predicts lung cancer incidence in a population. So, those are some of the common hypothesis tests that are used in public health, and many more. If you want to delve deeper into statistics, you can get to understand many more of these tests. So, what are the stages or the steps that you can take when you are doing hypothesis testing? Number one, you have to state the hypothesis. Define the null and the alternative hypothesis clearly. For example, the new vaccine does not reduce the disease rate or the occurrence of disease, and then the new vaccine reduces the occurrence of disease. Clearly define or state the hypotheses. Then select the significance level, or commonly known as alpha, that you want to use. So commonly in statistics, an alpha level of 0.05 is used. In most public health studies and research, indicating a 5% chance of rejecting the null hypothesis when it is true. Okay? So next, what do? We choose an appropriate test. Depending on the type of data and the type of study design and the type of outcome that we are studying and what we are really interested in, we choose an appropriate test. Remember the tests that we've looked at up earlier? So different statistical methods are used for different data types, different study designs, okay, and different outcomes. So you choose the appropriate test. You calculate the test statistic and the p-value. So you use that data, the sample data that you have, to compute the test statistic and then the corresponding p-value. We are going to talk about p-values in the next slides. And then after calculating that the statistic and the p-values, we make a decision. So if the p-value is less than the selected significance level, you reject the null and conclude that there is enough evidence to support the alternative hypothesis. So if the p-value is greater than alpha, then you fail to reject the null and conclude that there is not enough evidence to support the alternative hypothesis. So after making a decision, you draw conclusions. Based on the results, you're able to make conclusions about different interventions and policies and risk assessments, depending on what you are studying. Secondly, let's look at confidence intervals. I hope we are still following. Okay. So let's look at confidence intervals. What are confidence intervals? These confidence intervals ranges of values derived from sample data. So usually when you compute the test statistic, it comes along with confidence intervals. So these confidence intervals are used to estimate the true value of a population parameter within a specific level of confidence. So it represents how sure we are that the interval contains the true population parameter. So common confidence interval levels are 90%, 95%, and 99%, with 95% being the most widely used in public health. So you will rarely find the 90% and the 99%. Most of the time, 95% confidence interval is used in public health. So what are the key concepts to pick when you think about confidence intervals? So we have the point estimate. That estimates the sample estimate that we've been looking at, that sample statistic. So it represents the single best estimate of the population parameter based on the sample. For example, if the average systolic blood pressure in a sample is 200 individuals, okay, of 200 individuals is 120, then 120 is our point estimate. Okay, so within confidence intervals, we have that point estimate. And again, it is the single best estimate of the population parameter. So we also have the margin of error, which includes the range added to and subtracted from the point estimate to create the confidence interval. It accounts for the uncertainty in the sample estimate. So for example, if the margin of error is plus or minus 5, then our confidence interval might be 115 to 125 for blood pressure in our previous point estimate. So usually the point estimate is reported with its corresponding confidence interval. So let's look at the width of the confidence intervals. So the width of the interval reflects the precision of the estimate. Narrower confidence intervals indicate more precise estimates, while wider confidence intervals suggest more uncertainty. For example, 115 to 125 is a narrow confidence interval and it indicates more confidence in the accuracy of the estimate compared to this 110 to 140. You see, there is a big difference. So, the narrower the confidence interval, the more confident we are that our point estimate is lying between a narrower scale. Okay. The more confident we are in the results that we've got, the more confident we are in our point estimate. But if the confidence interval is wide, we are uncertain of where exactly it falls. Okay? So, what factors affect the width of these confidence intervals? What increases? What brings about the narrow confidence intervals? What brings about the wide confidence intervals? We shall look at just three, but there are many more that you can delve deeper into and get to understand. So we have the sample size, and just to note that large sample sizes always narrow the confidence interval and they provide more precise estimates. Having smaller sample sizes may widen the confidence interval, reflecting more uncertainty. So, when doing a study, you should be very conscious about the sample size under study and sample size under different groups under study. So, sample size calculation is also a key concept that you need to understand and maybe consult an experienced statistician to help you come up with a sample size that will provide more precise estimates for your study. So we also have variability in the data. So high variability in the data results in too wide confidence intervals because of increased uncertainty in the estimates. Low variability leads to narrower intervals, indicating more precise estimates. So lastly, let's look at the p-values. What is a p-value? It can be thought of as the probability that the outcome in the observed data would occur purely by chance. It quantifies the strength of evidence against the null hypothesis. How do we interpret these p-values? Because you will always come across p-values during your studies. Has anyone been able to come up with any p-values in a study? By show of hands, anyone who has come across p-values? Hello, hello. Are you still with me?
Yes, we are together.
Regina, have you come across p-values?
No.
Betty?
No,
Winnie? Winnie is not on. Hosea? Simon? Okay. Could you also register your presence in the chats? register your attendance in the chat, because it seems most people logged on and went away.
Yes, madam, a little concern from me here.
Yeah.
I'm in an area where there is no good network, so I disappeared, but not because I wanted to, but network got stuck. So if you don't see me on, that means my network.
It's okay. That is noted. Could you please register your attendance in the chats? It's part of assessment. So let's move on to the last section of our class today. How do we interpret these p-values? So small p-values, typically, because we talked about the 95% confidence interval being the most commonly used in public health. So typically the 0.05 level is used to determine how strong the evidence is against a null or how weak the evidence is against a null. So small p-values, I'm looking at basically those that are less than 0.05 suggests that there is a strong evidence against the null hypothesis. So we usually reject the null and go with our alternative. Remember, the alternative is usually what the researcher is looking out for in a study. So for example, if a study yields a p-value of 0.02 when testing the effect of a new treatment on reducing disease rates, it suggests that the treatment has a statistically significant effect on reducing disease rate, and the likelihood of this result happening by chance is just 2%. Okay? How about p-values that are greater than 0.05? Greater or equal to 0.05. These ones show weak evidence against the null. So when you get a p-value less than 0.05, we usually reject the null, and we usually suggest that there is no enough evidence to claim an effect or difference. So for example, a p-value of 0.08 is evidently greater than 0.05 of our class today.